Okay, class, today we're in lesson 1.3, ordering real numbers. Lesson 1.3, ordering real numbers. Your essential question: how do you order a set of real numbers? How do you order a set of real numbers? Comparing irrational numbers. Between any two real numbers is another real number. To compare and order real numbers, you can approximate irrational numbers as decimals. Once again, between any two real numbers is another real number. To compare and order real numbers, you can approximate irrational numbers as decimals.
You've heard about comparing apples to apples. That's great fun. Let's have some great fun on our own by comparing irrationals to irrationals. Compare square root of 6 plus 3 to 6 plus square root of 3. Now, in order to do that, we need to approximate the square root of 6 and the square root of 3, since we don't know what that simplifies to. So let's start with square root of 6. Now, what perfect square do we know that 6 is between? We know that 6 is between the perfect square 4 and 9. So let's use that as our comparison. So we have that square root of 4 is less than square root of 6, and square root of 6 is less than square root of 9. Now let's go ahead and simplify those. Square root of 4 is 2. And square root of 9 is 3. So square root of 6 is between 2 and 3. So we're going to say square root of 6 is approximately 2 and 5/10. Now let's move on and approximate the square root of 3 now. Again, what perfect square do we know 3 is between? Well, we know it's between 1 and 4. And so we're going to use square root of 1 and square root of 4. So square root of 1 is less than square root of 3. And square root of 3 is less than square root of 4. Now let's simplify. Square root of 1 is 1. And square root of 4 is 2. So square root of 3 is between 1 and 2. So we're going to say that square root of 3 is approximately 1 and 5/10. Now we're ready to look at the two expressions we're trying to compare, which we have right here, and I'm just going to write them on the right side. Okay, we already know square root of 6 is approximately 2 and 5/10. So we're going to replace that square root of 6 with 2 and 5/10. Now I don't know if it's less than, greater than, or equal to. That's why I'm writing that circle. We also know that square root of 3 is approximately 1 and 5/10. So let's go ahead and write the 1 and 5/10 instead of the square root of 3. Now 2 and 5/10 plus 3, that's 5 and 5/10. And 6 and 1 plus 1 and 5/10, that's 7 and 5/10. So, which comparison symbol should we use? Well, 5 and 5/10 is less than 7 and 5/10. And we just figured out that the square root of 6 plus 3 is less than 6 plus the square root of 3. Hey, apples to apples, irrationals to irrationals, it's all good fun. I'll see you next time.
Okay, now we're going to help out those who may be confused on how to go about figuring out the square root and the squares and how to set everything up properly. So this is what you have to do. You should list the numbers, something like 1, 2, 3, 4, and 5. Now what you do is you list those numbers, then you square them. 1 squared is 1. 2 squared is 4. 2 times 2. 3 squared is 9. 3 times 3. 4 squared is 16. And 5 squared is 25. Now, what you do is you put a square root symbol over each one of those numbers. Just like this. Square root symbol all the way across. Now look at the square root of 6. Which square root does 6 fall in between? Which square root does 6 fall in between? So the square root of 6 is going to be in between the square root of 4 and the square root of 9. So right there is where you put the 6. Now what's the square root of 4? 2. What's the square root of 9? 3. So the square root of 6 is going to be halfway between 2 and 3, which is 2.5. All right, now you can use that same list to determine the square root of 3. Where does the square root of 3 fall? It falls in between the square root of 1 and the square root of 4. So square root of 1, square root of 4, square root of 3 is in between those two. What's the square root of 1? 1. What's the square root of 4? 2. Once again, square root means what number is it when I multiply it against itself, it would give me 4. And that's going to be 2. 2 times 2 is 4. So the square root of 3 lies between 1 and 2. And what's halfway between 1 and 2? That's going to be 1.5. So that's how she was able to figure out what to work with. So in place of square root of 6, you would be putting 2.5. And in the place of the square root of 3, you would be putting 1.5. All right, so now 2.5 plus 3, that's going to be 5.5. And then 6 plus 1.5, that's going to be 7.5. So 5.5 is less than 7.5. So the square root of 6 plus 3 is less than the square root of 6 plus square root of 3. All right, so that should help you get right through example 1 out of your textbook to make sure you understand that. Okay, so to do example 1, we're going to use the same technique that we used in the previous video. All right, example 1, compare the square root of 3 plus 5 to the square root, to 3 plus the square root of 5. Compare the square root of 3 plus 5 to 3 plus the square root of 5. First, we approximate the square root of 3. So the square root of 3, remember our technique, we write down 1, 2, 3, 4, write down about 3 or 4 numbers in order. What's 1 squared? 1. What's 2 squared? 4. 3 squared? 9. 4 squared? 16. Put square root symbols around each one. Then we try to see where the square root of 3 will fit. Where square root of 3 will fit right in between the square root of 1 and the square root of 4. So square root of 3 would be right in between there. Now what's the square root of 1? 1. What's the square root of 4? 2. Halfway between 1 and 2 is 1.5. Okay, now look at the square root of 5. Square root of 5 will be between what two numbers? It will be between the square root of 4 and the square root of 9. So square root of 5 will be right here. So now what's the square root of 4? 2. Square root of 9? 3. So square root of 5 will be halfway between 2 and 3, which is 2.5. Okay, so now that we know the values, the square root of 3 is 1.5. The square root of 5 is approximately 2.5. So we plug in square root of 3. In place of that, I put 1.5 plus 5. 1.5 plus 5 is 6.5. Do the same thing below. 3, I bring the 3 stay the same. And then the square root of 5 is approximately 2.5. 3 plus 2.5 is 5.5. So you can see for this one, we got a value of 6.5, and for this one, we got a value of 5.5. So therefore, the square root of 3 plus 5, which is 6.5, is greater than the square root of 3 plus the square root of 5. And once again, this came out to be 6.5, and that came out to be 5.5. And that's how you attack those kind of problems. All right, now let's take a look at something like example 2, ordering real numbers. You can compare and order real numbers and list them from least to greatest. You can compare and order real numbers and list them from least to greatest.
You know, the real numbers come in all sorts of shapes and sizes, and actually they can be classified into different types of numbers. We have integers and whole numbers and natural numbers and even irrational numbers. I want to start off by just talking about the fact that if we have a list of real numbers, we can always order them from smallest to largest. So here's a whole bunch of real numbers. Let me introduce you to all of them, and then the question is, can we order them from smallest to largest? So let's see. First, there's the square root of 3. Now, what's that? Well, I don't know exactly the size of that, but I know, for example, it's smaller than the square root of 1. The square root of 1 is 1. And it's certainly bigger than the square root of 1, which is 1. And it's certainly smaller than the square root of 4. And the square root of 4 is 2. So this is a number that's between 1 and 2. That's all I know about that right now. Let's see what else we've got. Then I've got this decimal number, 0.945 stuff. All that stuff, as I go further to the right, has less and less significance. The key stuff is at the beginning. 0.9 tells me roughly where it is. This is just a hair under 1. So that's a number that's smaller than 1. Then I've got this one, 0.3 with a bar. And what that means is that that 3-digit repeats forever. This is a repeating decimal, 0.333333333 forever, never ending. Looks like a long thing, but it's just around 0.3 something. Then, of course, there's the famous 0. You all know what that is. I'm not going to say anything about that. And then finally, we have negative 5/4. And negative 5/4 turns out to equal, in decimal, negative 1.25. So now if we're going to order these things, certainly the negative numbers are the smallest. There's only one, so we have negative 5/4. Then we've got 0, because 0 is smaller than all the positive numbers. And then I've got these numbers. Now, what comes next? Well, this is between 1 and 2. This is just a little teeny bit under 1, and this is around 0.3. So the 0.3 comes next. Then comes the 0.94 stuff, and then comes this mysterious number that we know is bigger than 1. So there's a way of ordering the real numbers. Now, not only can you order the real numbers, but we can actually classify them. So let's take these numbers and take a look and see, well, what are they? So here's a list, and we have columns for the real numbers, the rational numbers. Those are the ones that can be expressed as a whole number divided by a whole number, or as a decimal that either terminates or is repeating. Integers, those are the numbers that are 1, 2, 3, 0, and also the negatives, negative 5, negative 16. The whole numbers, those are the numbers that start 0 and then go 1, 2, 3, 4, and so on. The natural numbers that start at 1, 1, 2, 3, 4, and so on. And the irrational ones, these are the sort of mysterious ones. They're the leftover numbers, the numbers that don't fit into any of these other categories right here. So let's try and see if we can actually check off all that apply for each of these numbers. So let's start with the second one. I'm going to leave the first one for last. So 0.3, now that bar, remember, means that it's 0.3333 repeating forever. It's a real number. And since it repeats forever, this decimal expansion, it's a rational number. But it's not an integer because there's this decimal part to the right of the decimal point. So it's not an integer, and therefore it's not a whole number, it's not a natural number, and since it's rational, therefore it's not irrational. So 0.3 with a bar is a real rational number. What about 0.945? Well, that decimal expansion terminates. It's a real number, and since the decimal expansion terminates, it's a rational number, not an integer, whole number, natural number, or rational. 0. 0's a real number. It's a rational number because I can write it as 0 divided by 1. And is it an integer? It sure is. Is it a whole number? Yeah, it's the first whole number. But it doesn't make the cut to be a natural number because the natural numbers start at 1. So no dice there, and it's not irrational since we already know it's rational. Negative 5/4, what do we have here? It's a real number. It's a rational because it's the quotient of two numbers. It's not an integer, not a whole number, not a natural number, not an irrational number. And that leaves us to the very last one. You've been waiting for this, square root of 3. Why did I save that for last? It's a real number. And it turns out that that's all we can say for sure right now.